Very good morning, good afternoon, good evening to all of you wherever you are in this part of the globe, and once again welcome to all the participants, all the students in the DADM 3 course under the NPTEL MOOC series. DADM means Data Analysis and Decision Making 3. We have already done DADM 1 and DADM 2, where DADM 1 was mainly in statistics, DADM 2 was in other non-parametric methods, and DADM 3 is more into optimization and operation research. This course total duration contact hours is 30 hours, which is spread over 12 weeks, and considering each lecture is for half an hour, the total number of lectures is 60, and each week we have 5 lectures of half an hour each. After each week we have assignments. So, we have already, if you can see from the slide, we are in the 10th week. So, means we have already completed 9 weeks and their assignments, and we are in the 47th lecture, which is the second lecture in the 9th week, and my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, if you remember, we in the last 2 classes we were just giving some results, and I have been mentioning quite a few times that I will go into the area of trying to understand the concept of branch and bound, which can be utilized very nicely in different type of problems. So, we will consider 2 type of problems. One is integer programming and one is binary variable values of the decision variables. Binary means it can only take 2 values like 0 and 1. So, a very good example would be, I am giving one thing like you want to build up a factory, and other option is you do not want to build up the factory. So, if you remember in that one of the problems where you had to basically build or manufacture the cards, they were in 1000 in numbers, and in case if it was less than 1000 it was not allowed. And in the other problem we had considered that a binary variable x was converted, x was the decision variable which was converted into binary variable in which was basically y. So, yi's depending on the number of i's of the decision variables are I is equal to 1 to n, y1 can be 0 1, y2 can be 0 1, and so on and so forth, either 0 or 1. So, this is the binary programming. So, we will consider a problem solution for that also using the branch and bound, and I will draw the graphs how the branchings are done, and it will be given in totality with the branches being highlighted as we proceed from step to step. And then hopefully in this week we will also cover some part of quadratic programming, and in the this is the 10th week. So, in the 11th and the 12th week we will basically considering the concept of reliability optimization, robust optimization, some part of stochastic programming. So, these are the slides which you have already gone through, but I will quickly go through them. This algorithm of branch and bound has already been discussed by giving the numbering as step 1, step 2, step 3, but I still rehash it in order to make it much more logical in the discussions which I will have with you, considering that we will be going into depth into 2 problems. So, branch and bound is the divide and conquer rule. So, you divide in which way you want to go, there would be only two paths, and one of them would be feasible. You will basically go further down considering the results. Results means not the optimal results. The decision variables are not non-binary or non-integers. You will go further down, try to basically break it down into 2 arms, and if they are infeasible or if their values are not increasing or decreasing depending on the type of problem you are trying to handle, these are the so called dead ends or not fathomable, you will stop there, and you will find out that as you differentiate the results for the integer variables and the decision variables which is z will come out automatically. So, in the branches I will write down which route you are going to take, what are the decision variable values and what are the z value, we will proceed accordingly. So, one divides a large problem into few smaller ones step by step, it goes like a hierarchy. And if you remember in DADM 2 we had done AHP, analytical hierarchy process, where we divided the primary decision into nodes and then proceeded step by step, but only change here leave apart the ranking system and all these things, only change here would be that the branches in AHP analytical hierarchy process could be more than 2, or consider that you have more than 2 number of decisions or criteria to consider, but here you will only consider 2. So, let me again read it. One divides the last problem into few smaller ones, and this is the branching part, while the conquering part is done by estimating how good a solution we can get for each smaller problems and then eliminating and considering the ones which are feasible. So, we will eliminate which are infeasible, consider only those who are feasible, and obviously we will try to reach the optimal solutions. Now, remember one thing, the word optimal solutions would not be with respect to the linear programming solutions, because if you remember I have been mentioning it time and again that you relax the problem, which you will do it in each and every step, solve it like a linear programming and then proceed. So, we are not going to compare the results with respect to the linear programming, we will only consider the results with respect to the integer programming, binary programming results which we get at different steps. So, because linear programming would basically have continuous decision variables, where if they are continuous they need not be integers. So, that would not suffice the actual problem formulation based on which we are proceeding. So, as we conquering is done by estimating how good a solution we can get from each small problems. For this, what we have to do is that we divide the problem further on into layers and layers until one obtains a problem that can be handled and solved, and we can compare the results accordingly. So, this is the bound means to what stage you will go, whether it is infeasible, feasible, unbounded, whatever it is, we have to stop at some stage depending on the stopping criteria. So, this is the first problem on branch and bound, and here we will consider there are two variables x1 and x2. Why I am taking 2 variables is because I will be able to draw and try to basically give a picture of stage by stage, like solve the problem and also show the feasible region and what is the optimum points. So, one side by side if they proceed. So, that means one after the other if they proceed you will get a better picture, but if I go to the higher dimension trying to solve them using 3 dimensional figures would be difficult. In the next problem, which is example number 2, we will have such a problem where the number of decision variables are more than 2. So, we have a maximization problem of minus x1 plus 4 x2. So, obviously, in this case as it is mentioned in the last point, which I will keep highlighting many of the points accordingly. So, it is mentioned that x1 and x2 are integers. So, what are the constraints? Constraints are minus 10 x1 plus 20 x2 less than equal to 22, less than type, and plus 5 x1 plus 10 x2 is less than equal to 49, and another one is that x1 is less than equal to 5. So, x1 has values if we solve the problem using the integer programming would be 0, 1, 2, 3, 4, 5, and for x2 it can be 0, 1, 2, 3, 4, 5 and continue till infinity, and but they are all integers, point 1. Point number 2, we are not taking values less than 0, not in the negative values, because as per the assumptions x values have to be basically positive, because that is very logical. Because if you are trying to formulate a problem where the number of trucks are important, where x1 is the number of trucks you are going to utilize to ship products from Bombay to different cities in East India, the number of trucks cannot be non-integers, they have to be integers. So, the problem is there are 2 constraints, 2 variables, maximization problem. Now, before I proceed, few things should be mentioned very categorically. When we convert the problem into linear programming, relax it, we will be always utilizing the same concept which we have studied in the first 5 or 6 weeks of the lecture, which was to do with the concept of how you solve the northwest corner method, the Vogel's approximation method, considering that you have the network problems, how you solve the linear programming, primal problems, dual problems, simplex methods, all these concepts will be utilized time and again. So, this is I would not repeat that, I will only highlight that where the integer programming and the branch and bound would be utilized. In between, whatever you do would all be the simple concept of simplex algorithm. So, this is the feasible region, the yellow one is the feasible region, and you have x1 and x2 drawn accordingly in the Cartesian coordinate, and this orange one I won't highlight it. Okay, I will highlight it using the orange color if it is yes. So, this is the objective function, and if you remember, for the maximization problem you try to basically move outwards, and the interior points where you will try to solve would be point A, which is the origin, point B, point C, point D, point E. Now, remember this vertical line BC and goes up is basically the fact where x 1 is less than equal to 5. So, the actual values of x 1 are 0. So, one value would be, I will use the red line. So, this is 1, this is 2, 3, 4, 5, and the corresponding values of x 2 are so this 3.8. So, obviously 3 value it should basically match. So, somewhere going like this. So, the actual points of solution in the feasible region, if it is a continuous variable, they are, I am repeating, A, B, C, D, E, but if you want to find, and all the inside region, these are the A, B, C, D, E are the points where you do the search, and the actual feasible region are infinite in number, considering that is the yellow region inside. But if we solve the integer programming points are, this can be a solution, this can be a solution provided is inside, this can be a solution, this is not. I am not going to highlight that this is not, because obviously it is not in the yellow region also, and also it is outside. But also remember, these points are applicable for the linear programming continuous variable case, not for the integers. This is not, this is yes, sorry, this is yes, this okay, this line should have been 3.8. This is technically a point which seems very interesting from the fact that x 2 is in integer, but x 1 which is 3.8 is not. This is can be a contender, can be a contender, can be a contender, can be a contender. So, we have to find out what is the point based on which we can solve the problem. So, now we will proceed. So, you have seen the problem, we have seen the overall diagram of the feasible region, both from the perspective of linear programming as well as the highlighted points are from the concept of integer programming, which are the feasible points where you will do the search. Now, we will start all the procedure on the branch and bound. So, first what we will do is that, if you remember, as per the algorithm which we had stated, step 1, step 2, step 3, so on and so forth, we will first find out the LP relaxed problem solution. So, what is the concept of linear programming relaxed problem solution would be very simple. The problem solutions remain the same. You first relax the decision variables, make them continuous and solve them, and the solution techniques are all what we have learned in linear programming, simplex method, so on and so forth. So, the problem formulation is like this: maximization of the same function, which is minus x 1 plus 4 x 2, such that constraints are also the same. Let me go one by one very slowly. Minus 10 x 1 plus 20 x 2 is less than or equal to 22, which is same. 5 x 1 plus 10 x 2 is less than or equal to 49, which is same. X 1 is less than 5, which is same. The main part which has changed, considering this is a LP relaxed problem, that is why I have highlighted in blue bold colored, is this one. So, this has been converted from an integer to a simple linear programming, considering x 1 and x 2 can be any values continuous. So, x 1 now can take any number between 0 and 5. including non-integers, and x2 can take any values greater than or equal to 0. Now, you solve it. You check the problem solution, the solution is already shown in the graph, just we finished checking the graph. So, you will just take one of the corner points, basic feasible solution, take the concept of the tableau, consider which is the exiting variables, which is the entering variables, continue solving it step by step, and it is easier for us to understand this problem because it is visible to us in 2D. Solve the problem, and the point where you will get the optimum solution is where x1 is 3.8 and x2 is 3. The actual value of z is 8.2. I will basically highlight it. The solution is this: z is 8.2, x1 is 3.8, x2 is 3. Now, you will ask the question, is it a solution for the integer programming? Answer is no, because x1 is 3.8, x2 is 3, which is fine, and z is 8.2. Now, what you will do? Now, here where you will take a decision. So, if you remember in one of the very simple brute force or logical method, or I can use the word brute force, in the sense I enumerated all the values and highlighted the points, that technically I would basically start with x1 can be either 4 or x1 can be either 3, and then solve the problem. That means, I have started the branching. So, this is from where I will start the actual branch and bound. Now, we consider two cases, because x1 is 3.8. So, x1 could have been 4 or could have been 3, and we will basically branch out from there. In one branch, you will take x1 as 4, x2 x1 as other is x1 is 3, and the value of x2, which is already 3, would be considered as it is, and we will proceed. So, now here is the graph. So, we have tried to differentiate the overall area. So, now my solution technically would have been like this. So, this first part yellow region is now a particular problem with an objective function with some constraints, and this yellow region, the first part, would be the overall feasible region if I solve using the linear programming part. And if I get solutions technically where x1 and x2 are integers, we will take that and keep it beside, and we would not proceed in solving that right part of the problem. I am just giving you the scenarios. And the left part, again you have a feasible region considering for the linear programming, solve it. If you get the decision variables as integers, then also you will stop, compare these two results and basically give the optimum one, which is maximum one, which is the easy, this scenario which I thought, which was a thought out experience sort of thing, a thought out process which I said is basically the best solution which I would have, because we do not have to go any more branching. But considering the right hand side and the left hand side, the decision variables, once you solve the linear programming, are non-integers, again you will branch them one at a time and then proceed accordingly. So, these are the second steps, third steps as you go, as you branch out. So, as just mentioned in the last slide, x1 values would be also considered from 0 to 3. So, that means actually they would be 0, 1, 2, 3, and the values of x1 on the for the other problem, for the other branch, would be 4 and 5, and x2 remains as the value of 3. But interestingly, this value of 3 which was there is now born into the feasible region. So, infeasible region. So, technically so initially this point was there, which is still true, this point was there, which is still true, this point was outside, I have not drawn it properly. So, it was not there. So, this point true, 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 true for the two sets. So, we will proceed now again. Now, we start the problem for the case for the first right hand side where x 1 is 4 or 5. Why 4 and 5? Why I am saying that? Check this. I am going to highlight it later on, but check this. Or let me highlight it, I can erase it later. This one. So, actually that problem which you need to solve in the right side of the region is still an integer programming with the following objective function and the constant. Let me read it and then it will become clear. So, objective function is max of minus x 1 plus 4 x 2, which is fine, such that constants is minus 10 x 1 plus 20 x 2 is less than or equal to 22, which is fine, because these are the constraints which you want to take. This one x 2 is greater than 0, that means it will be 0, 1, 2, 3, 4 till infinity, all integers. X 1 would be only 4 and 5. Now, having said that, this is an integer programming, we will relax it, and that relaxed LP is written here in front of you, which is maximization problem remains the same, objective function does not change, constraint 1 does not change, constraint 2 does not change. What changes are the following? This I said I will remove, I will highlight. This is the continuous variable for x 1 between 0, 4 and 5, any values inclusive. This is the values of x 2 starting from 0 to infinity. Now, again you solve it using the linear programming concept. Once you solve it, your optimum solution is like this. You get x 1 as 4. So, your object function is x 1 is 4. So, it is here somewhere here. So, x 1 is 4 and x 2 is 2.9, but obviously x 1 is now integer, x 2 is not integer. So, you have to solve it and basically solve it means go for the next step. So, there is more branching is required, whether we want to proceed in that branch area or not would basically we will be considering in totality as we consider all the branches and the bounds. Now, this is the solution. Now, very interestingly, this red line which you see, oh sorry, I should not be utilizing this one. This red line which you see is the same one which was earlier for the objective function, same objective function, when the overall feasible region was the total yellow region. So, it has just, I have just brought it down in order to make you understand that when it crosses this overall area, the boundary area which is yellow in the right hand side, and those points are actually these points. You remember initially what was A, this was B, this was C, this was D, this was E. Let me check whether I have done it right. A, B, C, D, E, yes. But now D actually is not true. This is a new point which is D1, where we are trying to find out the optimum solution, which was already stated. So, optimum solution is now Z is 7.6, x 1 is 4, x 2 is 2.9. So, this is the overall area. Now, we take, I will tell you. So, we had taken values of x is greater than 0 here, but if you consider here, these values are only applicable for x is x 2 is greater. So, x 2 being, let me check, x2 being greater than 0, but if you consider x2 values can be 0, 1, 2, 3, 4, it will go on. So, I need to basically change the search space of x2 considering that x2 has now 2.9, which means x2 can either be in the second branch, it can be 3 or 2. So, technically x1 was basically 4 and now x2 was a non-integer, now again the branching would be done. So, first we will take the value of 3. So, here you see x2 is 2.9, so hence it will be 3 considered in the one of the branches. Let us put it, our actual problem when in the relaxed or the LP problem formulation is like this. I will come back to the actual integer problem formulation once I repeat the relaxed formulations. So, relaxed LP formulation is max z minus z x1 plus 4 x2 remains the same, minus 10 x1 plus 20 x2 less than equal to 22 remains the same. Same means as with respect to the earlier constraint. 5 x1 plus 10 x2 is less than equal to 49 remains the same. x1 is continuous remains the same in the linear programming relaxed form. What is interesting to note down is that we have taken x2 divided into 2 regions, 2 less 3 more. Here we are taking x2 is greater than 3, and if you solve it there is no feasible solution, which is very interesting to note down from the diagrammatic point of view also. Go here. The point of 3 when x2 is 3 is not inside the feasible region. So, diagrammatically also you see it is not possible, it is outside the feasible region, and when you solve it also you would not get any feasible region. Feasible region concept we have already done in linear programming and simplex method. So, you will get it verified by solving the problem. Here I just wanted to highlight the diagrammatic perspective also, that is why I mentioned when we started the problem we will take a 2-dimensional problem. So, for us to understand it clearly. So, the problem would have no feasible solution. So, obviously we will try to not proceed. Now, okay, by the way, what was I would come to the other solution in the subsequent talk which is continuing. The non-relaxed, I would not be using the word non-relaxed, but the integer programming actually is maximum problem is the same, constraints tools are the same, while x1 has only values 4 and 5 and x2 has values of 3, 4, 5, 6 until infinity. So, that has been relaxed and we have obtained this and this for the linear programming. So, now what is left is that as we consider 3, we will consider also x2 in the integer programming values of less than 2, less than equal to 2. So, that means it we will consider the values of x2 as 0, 1, 2 and x1 will remain as 4 and 5. We will relax it, continue by solving the linear programming and give the solutions accordingly. So, we will proceed in the branch and then take a decision whether there is a bound, we stop it and proceed in the other direction. Thank you very much, and we will continue discussing this problem and the other branch and bound problem in the subsequent 3 lectures, definitely in the 10th week. Have a nice day and thank you very much.